In this module, we will be seeing the different types of stress experienced by various machine elements. To start with, we will see the axially loaded member. That is, if we have a specimen like this, which is loaded by a load P, as shown here, we have seen earlier that when this rectangular specimen is subjected to load, it undergoes a deformation and there is an elongation by an amount dl. And we have seen that the stress in this case is given by P by A and the strain is given by dl by L, where dl is a change in length and L is the length of the specimen. And if the loading is done within the elastic limit, we have the Hooke's law, which is nothing but sigma is equal to E epsilon. So from this we get dl is equal to PL by AE, where dl is nothing but the elongation. This system is very much analogous to a spring system, where load is applied when the load applied is P, we have the stiffness of the spring K given by F, the force by elongation. Stiffness of this spring is given by force by elongation, where K is nothing but the stiffness. If this analogous we apply to the axially loaded member, we get that K is nothing but force by elongation. In our case, the force is given by P and the elongation is given by dl. So that comes out to be AE by L. Therefore, we can write the stiffness of our member, stiffness of this axially loaded member is given by AE by L. The advantage of the analogous spring system is that it is easy to find the deformation for the composite systems, where you have a specimen in series and parallel. What I mean by series is, when we have two shafts in series of length L1, area A1 and material E1, and the second shaft of length L2, area A2 and modulus E2, subject to the load P. If we apply the concept of spring, we can represent as two springs of stiffness K1 and K2 loaded by a force P. In this case, what will be the elongation? Elongation is given by P by K effective. And we know that for springs in series, K effective is given by 1 by K1 plus 1 by K2, the whole inverse. So in this case, the effective stiffness will be given as, where K1 is nothing but A1 E1 by L1 and K2 is nothing but A2 E2 by L2. So effective stiffness is given by L2 by A2 E2 plus L1 by A1 E1 whole inverse. And the elongation of specimen is given by P by K effective, that is nothing but P into L1 by A1 E1 plus L2 by A2 E2. This way we can easily find out the elongation of members in series and also in systems in parallel. When we have two shafts in parallel, like this. And loaded by force P. In this case, we know effective stiffness is equal to K1 plus K2, that is equal to A1 E1 by L1 plus A2 E2 by L2. Therefore, the elongation is given by P by K effective, that is nothing but P by A1 E1 by L1 plus A2 E2 by L2. This way we can easily find the elongation of systems in series and parallel if we have an analogy with the spring system. Now we'll see the stresses and deformation and bending of beams. If we have a cantilever loaded beam, loaded by a load P, you have the bending equation which says sigma by y equals m by I is equal to E by R. This is an important equation, this is a bending equation where sigma is the bending stress on a fiber at a distance y from the neutral axis. M is the bending moment at that section. I is the moment of inertia. E is the Young's modulus. And R is the radius of curvature of the beam. And the shear stress in the beam tau is given by VQ by IB, where V is the shear force, Q is nothing but integral of y dA, I is the moment of inertia, and B is width of the beam. This is about the bending of the beams. Similarly, we have torsion of shafts. The torque T is applied to a shaft shown here. You have the torsion equation given by tau by R is equal to T by J is equal to C theta by L. This is the torsion equation where tau is the shear stress at distance R from the centroid. T is the torque, J is the polar moment of inertia, C is the rigidity or shear modulus, theta is the angle of twist, and L is the length of the shaft. That's about torsion of shafts. Then we have buckling of columns. Columns are mechanical members with high L by D ratio and subjected to compressive load, like this. And the maximum load which can be taken by the column is called the critical load, and this depends on the boundary condition used. Depending on the boundary condition, we have different values of the critical load. For both end hinged, we have critical load as pi square EI by L square. One end fixed, one end free. We have P critical as pi square EI by 4L square. Both ends fixed. We have P critical as 4 pi square EI by L square, and one end fixed, other end hinged. We have critical load as 2 pi square EI by L square. That is about buckling of columns. Now we come to the pressure vessels. Basically thin pressure vessels. In that we have two categories. One is a cylindrical pressure vessel. In this we have circumferential stress or hoop stress given by PD by 2T, and axial stress sigma given as PD by 4T. And in spherical pressure vessels, we have seen that circumferential stress is given by sigma is equal to PD by 4T. In spherical pressure vessel, your axial stress also will be sigma is equal to PD by 4T. Both stress will be the same. Now we have seen the stress experienced by machine elements subjected to different kinds of loading. For example, for a beam with a transverse load, we know the normal stress given by the bending equation. And if it is a shaft with a torque T, we know what is the shear stress, so we can design for the shear stress. And if it is an axially loaded member, we know again what is the normal stress sigma given by P by A. Now, what happens when we have a combined loading? That is, a combination of load acts on member. For example, if I am having a shaft, circular shaft, subject to a torque T as well as a load, transverse load T. Here I have a combination of normal stress, nothing but the bending stress, and shear stress due to a torque T, and bending stress due to a moment M. So in this case, what will be the maximum normal stress? And what will be the maximum shear stress? And in which plane does the maximum normal stress and maximum shear stress acts? To get the answer to these questions, we will see the next module on principal stress. So that completes the third module on stresses in machine elements. Here we have basically seen what are the stresses which comes in the machine element subject to different kinds of loading. This is just a recap of what we have seen in strength of materials. This will be useful when we go to the next module on the principal stress, which deals with how to, given a combination of loads acting on a system, how to find the maximum normal stress and maximum shear stress, and also the planes on which the maximum normal stress and maximum shear stress acts. This we will see in the next module. Thank you.